Hello. So far, we've been looking at the design of a optical receiver for an optical sensor. So we started with looking at the front end, the PIN photodiode, APD photodiode, how to extract current from that when light is incident on it, how to extract current efficiently from those photodiodes when light is incident on it, how to amplify them and so on. So how to build your optical receiver effectively. And in the last lecture, we actually looked at signal to noise ratio issues. Specifically, we looked at the typical noise sources as far as a receiver is concerned. So now it's time to take a step back and quantify the performance of an optical sensor collectively. Okay. So what do I mean by that? Well, how do you tell that one sensor is actually better than another, right? So how do you compare two sensors? Okay, so you need to have some quantification as far as the sensor performance is concerned. So that's what we're going to be talking about. What are the typical performance metrics of an optical sensor? So when we talk about performance metrics, so what we are saying is how to quantify the sensor performance, right? And then, what are the typical type of metrics that you can think of? So one would be obviously the measurement range. So range, or in some cases it's also called the dynamic range of the sensor. Okay. Next will be the minimum detection limit. So what is the minimum quantity that you're going to be able to measure in terms of the sensor? Then you have things like sensitivity. How well the sensor responds to some change in the parameter that you want to be measuring. And then you have things like response time of the sensor, and more importantly perhaps, because most of these are talking about some deterministic quantities, but there is a certain level of uncertainty involved with any of your measurement. Okay, so how do you quantify that uncertainty? Okay, so then you start thinking about things like accuracy, and then you talk about precision or repeatability, right, and so on. And of course there are other things like the linearity of the sensor, and then if there is any hysteresis effects and so on. So there could be other parameters also, but you'd find that those are all not very common. So there are certain applications where the way the sensor is designed, it exhibits hysteresis, so you need to quantify the hysteresis and so on. But those are some special cases. So let's look at how these quantities would work. And to give you an example, let me actually go to a commercial sensor that's available in the market. Okay, so this is an ammonia gas sensor. So this is actually made by I think Honeywell. So what are the typical specs do we see for this gas sensor? First of all, it's not an optical sensor. I'm just picking something up out of the blue just to give you an idea about the sensor performance metrics, and just to give you examples for the kind of numbers that you're likely to see whenever you pick up the specification sheet for a sensor. So it has got measurement range. It has got well, there is a maximum overload also defined for this. In this case, it's a sensor that works up to a certain range, and you can probably push it to a higher value, but beyond a certain point, it might actually suffer some irreversible damage. So that's what you talk about, the overload limit, right? But so there is a difference between this number and this number. So what's happening between that? So what we are saying is, when we say 0 to 100, that's the range over which rest of the specifications are supposed to work very well. And beyond that, you might still get a response, but those won't conform to the other specifications. Okay, so they are not actually mentioned as part of the measurement range. Okay, then there is a lower detection limit which says, okay, I'm not going to be able to do a good performance below that, typically because of noise issues that we talked about previously. So you'd have a limit like that, and then there is actually a sensitivity number. So the sensitivity is, in this case, you have a certain concentration of the ammonia gas, right, and you're trying to extract a parameter at the receiver, and that parameter is actually for an electrochemical sensor. It's a current, this electrochemical current that comes about. So so the sensitivity is defined with respect to the slope of the current that you get for a unit change in the concentration of the ammonia gas. Okay, and then there is actually a response time. So yeah, what is the typical time over which you can, beyond which you can actually get reliable readings. So that's what readings that conform to, once again, all the other specifications. So that's what we talk about as a response time. And then there is actually some offset and zero shift and all that. Those again are not typical. But then you come to accuracy, right? Which is I will define what accuracy is, and then there is repeatability. Okay, so how well, if you do the same measurement multiple times, how well can you actually be able to reproduce the results that you are getting. Okay, so those are some typical numbers, and of course there are some other special numbers. In this case, you have what is called cross sensitivity data. It's very, very important that when you're trying to pick up one quantity, how sensitive it is to some other quantity. In this case, we are talking about a gas sensor, so you're supposed to pick up only ammonia, but then your electrochemical process in this case may be sensitive to other gases as well. So so this is sort of the specification with respect to that, and so what we see is that hydrogen can cause the largest sort of uncertainty in your reading. So you might, if you have such a level of hydrogen, then you might actually have a significant reading on your sensor, which might confuse your reading, because your sensor reads say 200 ppm, some current value corresponding to 200 ppm, and then you don't know whether it's because of ammonia or whether it's because of hydrogen, or how much of it is due to ammonia, how much of it is due to hydrogen. So there is a uncertainty that comes into the picture. So cross sensitivity for a lot of practical applications is one of the key parameters that you want to look at. It is not good enough if you make a sensor that just measures what you want to measure. It is also important to quantify how well it is able to measure in the presence of some other changes, some other quantities that are present in the environment. Okay, so just wanted to give you a general idea of how to read specification sheets and what are the typical parameters that are mentioned in a specification sheet. So let's go back to where we are at, and let's actually try to quantify all these parameters, all these metrics in a little more deeper way. Okay, so the first one is the measurement range. So to quantify that, let's actually look at like what in this case an ammonia sensor would do, right? So you basically have as far as this sensor is concerned, you have your concentration, which is expressed in parts per million. Okay, and then you have a current that you are reading, and like we saw in the specification sheet, it could be in the order of nanoamperes. Okay, so we are basically looking at some change in current as a function of concentration. Hopefully it's a linear relationship. We will see why linearity is important, but you may be making measurements like this, and so on. So at different concentration values, you have different measurements done. So if you do a linear fit to that, so it might look something like that. So then the question is, what is measurement range? Well, measurement range corresponds to the minimum, the range between the maximum value that you can pick up and the minimum value that you can pick up. So let's actually look at this. Let's define that. So measurement range is maximum value to minimum value over which the sensor works reliably. Reliably as in it meets most of the other requirement, other specifications also. So in this case, what we see is we can say it starts working from here, and then up to this point it's able to maintain this linear relationship, and if you try to push this even further, like we saw in the specification sheet, it might respond, but it may not respond, it may not conform to these specifications. So so this is your measurement range in this case. Okay, so your measurement range is between this and what we have over here, right? Of course, you may argue that the measurement range may not be exactly starting from 0. Why? Because there is some uncertainty involved in the measurement, and that uncertainty may be built into the sensor, meaning there is a certain noise floor that you have below which you are not going to be able to pick up any measurable signal. So that noise floor would be basically somewhere like this, right? So you would say that there is some when you're measuring the current, when you're looking at the display, even without any ammonia present in the environment, you might have the display actually vary between in the last few digits of your few bits of your ADC maybe. So the last few significant least significant digits, maybe there's some variation. So that actually puts a cap on this measurement. So you would say that if that's the case, then this actually corresponds to what is called the minimum detectable limit, right? So as the name itself suggests, the minimum detectable limit once again talks about minimum value that can be measured once again in a reliable manner. So it conforms to all the other specifications. Okay, so that's actually the minimum detectable limit, and in some ways you may argue that when I'm talking about measurement range, it should not be from 0, it should actually be from the minimum detectable limit. And of course you'd be right, because for all practical purposes the sensor is useful only beyond that minimum detectable limit. Okay. Then there is sensitivity. And this is actually in terms of the usage of that word, sometimes it may be a little confusing because of the fact that when we say sensitivity in an optical communications perspective, right? When people talk about sensitivity, they're talking about the minimum power level that is that should be incident on the receiver, so that you can maintain a certain bit error rate in a digital communication system, right? So it's you basically say you need a bit error rate of 10 power minus 9. So to achieve that bit error rate, what is the minimum power that should be incident on the receiver, and that's what we call as the receiver sensitivity. Okay, so that's a term that's very widely used in optical communications, but in measurement in sensors, sensitivity actually takes a different sort of definition. The sensitivity here corresponds to the slope of this line. So for a certain change in concentration, what is the corresponding change in current that you get? Okay, so it's basically the slope of this line over here. So this basically dy over dx. Okay, where dx corresponds to this one and dy corresponds to change in this. Okay, so clearly more sensitive the better, because then you can actually get a nice change in the in your display for a small change in the in the parameter that you're trying to measure, in this case the concentration. But you have to be careful about that, because if it is highly sensitive, it might actually fill your ADC very quickly. Meaning you have a certain say, let's say you have a milliamp of current, and you convert that to say you have a factor of 10 power 3 with your transimpedance gain, and then you convert that to a voltage. So milliamp becomes more like a volt, right? So your typical ADC swings between say 0 to 1 volt, and then you'd fill the ADC very quickly. Okay, so then beyond that, your ADC is not able to read any value. Okay, so that actually in some cases corresponds to the maximum value of your measurement range. Okay, so there is actually a trade-off between the sensitivity and the measurement range. If you want high sensitivity, maybe your measurement range will be limited because you're not able to support such a large change in the in this case the current from nanoamperes to milliamperes. So that's actually 10 power 6 units, and what actually determins the smallest unit you can pick up, that would correspond to the least significant bit of your ADC. So if it's a 10-bit ADC, then you say 2 power 10 levels you can support. So that corresponds to, if you're swinging from 0 to 1 volt, then that corresponds to roughly a millivolt is what you can think. So that's actually corresponding to 30 dB. So from millivolt to a volt you can support, right? So those are some of the considerations that you have. But in this case, what we are talking about sensitivity is change in ratio of change in measured value to the change in the measurand. The measurand in this case is actually the concentration. The measured value is in terms of current. Okay, so that actually determines the sensitivity. Okay, so this, all these are fine. Now what about response time? So once again, when we are talking about response time, we are saying, okay, whenever, so we are switching with switching to something with respect to time. So here we are once again measuring the current, but we are measuring some change in this current, okay, for a unit change in concentration. So let's say you start with one concentration level, right, and at this point you are actually jumping to another concentration level. Okay, now if you make multiple measurements or measurement over time, you might actually see something like this. At this concentration you have something like this, but when there is a shift in the concentration, so it starts responding like this, then maybe it overshoots this, then maybe tries to settle down at a particular value after some time. Okay, so if you actually connect these, you'd probably get something like this, and then it settles to a value. Now, the response time now is defined as from the time this change in concentration happened. So what's happening here is basically at this point you have a change in concentration, right. So you have a change in concentration, and then how long does it take to capture that? Well, it basically oscillates around a certain value, and then finally it settles down to some steady state value. So you would say that at this point it measures a reliable number. Okay. So then this is what you call as the response time. So response time is the time taken by the sensor to settle to a reliable value, okay, to settle to a reliable value when there is a change in the measurand, okay, when there is a change in the measurand. Okay, so that is actually what we call as response time. Okay, and of course you want typically a fast response time, which means that what actually controls response time? Well, you would say that the receiver bandwidth is probably one of the most important things, that will actually limit the response time in a fundamental manner. So you need to have as quick a response as possible, which means we need to have as high a bandwidth as possible as far as your receiver is concerned. So the receiver bandwidth has to be very high. Then finally we come down to quantifying accuracy and precision. So let's actually try to go into a new page and try to do that. Let me actually show you 4 different scenarios, and let's see how accuracy and precision would work. Okay, what do we mean by accuracy? What do we mean by precision? Both of them in some ways talk about the uncertainty in our measurement. But let's say this is my target value. Okay, so that's what I am supposed to measure. So I have a certain concentration at a certain time, and I should measure that value with respect to the current. And so I'm actually going to try to represent this in 2 dimensions. So so let's see how this works. Now you could have a case where you are making measurements, and the in this case, let's say it's with respect to position. So this is my target value, but I make a measurement where it's roughly like this. Okay, it's a bunch of points around the target value. Okay, so that could be one scenario. Then there is another scenario where your target value is like this, but then you have a bunch of points very close to each other that are somewhere over there. Okay, so this is another scenario. Okay, then yet another scenario could be where you have the target like this, and then your measurements are like sort of all over the place, but they are also at a different place. Okay. And finally, there is a case where you have the target like this, and then all your measurements are around this. Okay. So, it's very easy to tell which is the most preferred case. Well, you directly say that, okay, I want, if I am looking at my probability density of where my points are, my measured values are, right, with respect to whatever quantity you are measuring, you would say that, okay, this is my target, right, and with respect to the target, I have basically a probability density like this. Okay. So, it's fairly close to the target, and then the probability density also works out to be around that value. Now, the same thing if I plot here. So, this is probability density of my measured values, and once again here we are saying, okay, this is where I am with respect to the target, right, this is my target, but my measured values are still bunched together, but they are off from my target value. Okay. So, but they are still nicely bunched together. Then compared to that, if you look at what's happening over here, so this is my probability density once again as a function of the measurement space, the values of my measurement. This is my measured value, and my target is here, but my measured values are like spread out around my target. It's widely spread around my target. And finally, we come to this case. If I look at the probability density once again of my measured value, you have the target here, but then it's nice and broad away from the target. Okay. So, with respect to all of this, let's actually look at what is let's define what is accuracy and what is precision. Well, accuracy corresponds to this deviation, okay, this deviation from the target value. Okay. So, that is what we call as accuracy, right. So, we have a certain we are expecting a certain value, but your your sensor actually gives you a different value of measurement. Okay. So that but then there is not a whole lot of uncertainty around that measurement. So that's the good part over here. There's not much uncertainty. So which is actually the worst case of all of this? Well, the worst case would correspond to this, because my accuracy is very poor, but it's also accompanied by a wide variation in my measurement, and that wide variation, I'm just making multiple measurements here, and it's giving me all those values. Okay, that wide variation is what we are talking about in terms of precision or repeatability. So this is actually a case where we say this is poor accuracy, poor precision, or repeatability. This is actually the worst case, and this is like high precision as well as accuracy. This is a case of high accuracy because the central value is still reasonably accurate, but this is basically poor precision because there is a lot of uncertainty in terms of the measurement. And here this is actually poor accuracy because my sensor value is the measured value is off from the expected value, but it's got high precision, high level of repeatability. You keep making multiple measurements, you get the same value. Okay, so that's actually corresponding to fairly high precision. Okay, so those are the different cases that we can see. Hopefully that actually gives you some idea of what we mean by accuracy, what we mean by precision or repeatability. It also brings up the question, which is more important to you, accuracy or precision? Okay, well, that's a tough question. In an ideal world, you want both, right? So you want your sensor to be both having high accuracy as well as high precision, so you can make your measurements like you do in this case. Okay. However, if you were to compromise on something, you could potentially take a case like this, where you say this it's poor accuracy, all right. So it basically says, okay, I'm expecting 100 ppm and it shows me 120 ppm. But if it is scaled, if it is 50 ppm, it's actually showing 60 ppm, right? Then it's actually scaling, right, in terms of the measured value. So if it is some scaling error like that, that is impacting your accuracy, that is something that we can handle. All you do is you do a next step is calibration. So through calibration, you can actually move. If you measure at that value, you can actually make it you can do your process your data and say this is actually, it means this value. Okay, so that way poor accuracy could be handled by calibrating your instrument, but you cannot do anything about poor precision, because that is actually talking about a random error. Okay, there is very is very low level of repeatability in your measurements. Every time you do it, it's actually giving you a different value and all that. Okay, so there's not a whole lot you can do from a sensor perspective about something like that. But what you could possibly do to deal with it is to make, instead of making one measurement, you make 10 measurements and then you take the statistical mean of those measurements and you say, okay, that is actually the value that it should correspond to. So obviously in a case like this, if you take a statistical mean, that would converge at the target value. Okay, so poor precision would have to be dealt with by taking many more measurements than what you plan to do. Okay, so hopefully that gives you a general scope, general idea of all the different sensor parameters, and we will go on to look at actual design of specific sensors, and when we do all these sensors, we will come back and revisit these quantities and see how well each of those sensors are performing.